Hello, everyone. Today I will introduce our paper, Bidirectional Copy-Paste for Semi-Supervised Medical Image Segmentation, commonly referred to as BCP, which has been accepted by CVPR 2023. This paper focuses on the semi-supervised segmentation task. Typically in semi-supervised scenarios, we assume that labeled and unlabeled data is drawn from the same distribution. However, due to the inconsistent and unsymmetric learning paradigms between labeled and unlabeled data, there may exist a problem of empirical distributions mismatch in real-world scenarios. To address this issue, we have designed a simple and effective bidirectional copy-paste method, which achieves state-of-the-art performance on 3 public medical segmentation datasets. Notably, as demonstrated in the figure, on the ACDC dataset with only 5% labeled data, our DICE score exhibits an improvement of 21 percentage points. The first part is motivation. Here we show the traditional self-training framework, which is a classical semi-supervised method. There's usually a supervised loss to leverage labeled data, and also an unsupervised loss to use unlabeled data. Self-training uses a teacher network to get the pseudo-labels for unlabeled data, which are then used to supervise the unlabeled data. Please note that the implicit assumption in this process is to fit the distribution of the entire dataset with labeled data, and then predict the outputs of unlabeled data under this distribution. What are the drawbacks of this approach? Let's use this figure to illustrate. The curve graphs in this figure are all kernel density estimates used to describe data distributions. Figure A shows the distribution of the entire dataset, Figure B shows the distribution of labeled data only, and Figure C shows the distribution of unlabeled data. Due to the limited number, it's difficult to fit the true distribution of the entire dataset only with labeled data. In the traditional self-training framework mentioned earlier, the inconsistent and unsymmetrical learning paradigm between labeled and unlabeled data means that Figure B is used as Figure A, resulting in the problem of empirical distribution mismatch. To further illustrate this, let's use some numbers to make it more intuitive. In this figure, we compare our method and the models trained by 4 other papers by testing their DICE scores on the labeled and unlabeled data training sets. It can be seen that the DICE scores of the labeled data sets for the 4 other methods are much higher than those of the unlabeled data sets, indicating that these methods have learned enough knowledge from the ground truth of the labeled data but discarded a lot when transferred to the unlabeled data sets. In contrast, our method significantly reduces the gap between these 2 scores. The second part of the motivation is that cut mix can be used better. As a data augmentation method, cut mix has the potential to enable the unlabeled data to learn semantic information from the labeled data. Its method is to crop a part of an image and paste it onto another image. It is often used as a strong data augmentation method in semi-supervised segmentation. We borrow the framework of a paper to illustrate. Cut mix is often used as a strong data augmentation in consistency learning, but this approach only applies cut mix to 2 unlabeled data, and then uses inaccurate pseudolabels for supervision, which cannot fully utilize the advantages of cut mix. Many methods of using cut mix between labeled and unlabeled data have also been proposed, but they mostly use the ground truth of labeled data to paste the foreground of the labeled data onto the unlabeled data, and the learning paradigm between labeled and unlabeled data is still inconsistent and unsymmetrical. To address the aforementioned issues, we propose an amazingly simple yet effective method based on self-training framework, bidirectional copy-paste. For the student network, our input not only pastes the labeled data onto the unlabeled data, but also pastes the unlabeled data onto the labeled data. The supervisory signal for its output is a mixture of ground truth and pseudo-labels, which are combined based on the way the labeled image and unlabeled image are merged. The pseudo-labels are obtained by feeding the unlabeled data into the teacher network. For the network updating method, the student network uses gradient backpropagation, while the teacher network uses exponential moving average, EMA. The third part is the experimental section. Here we present our experimental results on 3 publicly available medical segmentation datasets: the LA dataset, the NIH Pancreas dataset, and the ACDC dataset. It can be seen that our method significantly outperforms previous state-of-the-art methods on all 3 datasets. Here, we present the KDE plots of several methods on the left to demonstrate that our method can better align the distributions of labeled and unlabeled data, From top to bottom are the performances of 3 classes of AC/DC dataset. On the right, we show the ablation experiment on 5% of the AC/DC dataset. The top row represents the traditional self-training method, and adding BCP alone leads to significant performance improvement. We also employed other strategies to enhance the quality of pseudo-labels. Please refer to our paper for more details. Thanks for your listening.